about the last time you're stuck in bumper-to-bumper traffic on the M25 or any other motorway? It's frustrating, it's slow, but ultimately it's manageable because everyone is moving in the same direction, brakes exist, and you can see the car in front of you. Now, imagine that same level of congestion, but the highway is Earth's orbit. There are nearly 40,000 tracked objects, from massive satellites to tiny flecks of paint, all hurtling through total darkness and upwards of 17,000 miles per hour. There are no brake lights, no headlights, and a collision with a piece of debris the size of a coin can instantly destroy a multi-million-pound spacecraft. Humanity has a crowding problem, and it's happening right above our heads. So, how do you police, monitor, and protect an invisible highway system when ground-based radar can no longer keep up? Welcome to the Turing Podcast. I'm Amelia Jabry.
And I'm Dr. Victoria Nockles, and I head up the Defence AI Research Centre, or DARE, at the Alan Turing Institute. Today we're exploring space domain awareness and a revolutionary new technology that is looking at a radar sensor where we're imaging from space to space. And we're using this to be able to understand the congestion in orbit.
Joining us to unpack how this incredible, all-weather, day and night active sensing technology works is Marina Gashinova, Professor of Radar Systems Engineering at the University of Birmingham. Marina, welcome to the podcast.
Thank you very much, Amelia and Victoria, for inviting me to this podcast. I'm quite excited. So you wanted to talk about sensing capability which we are developing, yeah?
Yeah, and there are a few definitions we want to unpack first, and I feel like maybe the first definition we want to unpack is space domain awareness. I know what all those words mean in isolation, but what does it mean altogether?
So I will start and Victoria will continue. Space domain awareness. As you rightly said, we have an enormous number of resident space objects, which include active satellites, defunct satellites, space debris, and so on. So we want to understand how they move, if they are healthy, if there is a traffic congestion indeed, and if we are now moving a little bit to the defense area, if there is some hostile activity in space, which is starting to be quite significant, because in general, everyone is now racing for dominance in space. So the future economy will be like an Earth and space economy. And this is where we want to monitor what's happening there. So we want to make a space mapping similar to street maps, which Google makes, but we are going to do it in space. So this means that we will be aware about all these activities. We will know how the satellite look like, and we will know it from much shorter distance and from the aspects which are not available from the Earth for ground-based radar or ground-based telescopes.
Yeah, so there is less space in space at the moment, or at least in certain parts of space.
Yeah, because you can talk about the space being vast, but the space traffic is not vast. It's actually all going to prescribed trajectories. So we have orbital belts, which are occupied more than other. For example, Starlink occupy few shells at very certain altitudes, such as 430 kilometers, 500 kilometers, and so on. Then we have a medium orbiting satellites, something like from 1,200 kilometers and above. And then we have a GNSS, our GPS, lovely GPS, 22,000 kilometers. And then we have the most remote one, 36,000 kilometer satellite at GEO or geostationary orbit as well. So this means that it's vast, the space, and some parts of the space is still empty, but some is so congested, especially the lower is the orbit, the more satellites we will have there, especially with the Starlink one.
Yeah, so I guess we've established the where. We're in the lower Earth orbit, and that's the bit that's really congested. But then how do we monitor that? How do we track that?
So a lot of the traditional approaches use telescopes, and so you have a ground-based telescope that's looking up that has a very limited field of view. And the problem with that is you need a distributed sensor network. You need to be catching objects if you're using solar illumination. So if you're trying to get the brightness of an object and see how that varies, then you need to be able to catch it within a certain angular view to be able to catch glints on a satellite, to be able to assess how it's moving and where objects are located. Ideally, rather than just having a ground-based sensor, we want to be starting to use space-to-space sensors as well. So we want to be able to cover the entire low Earth orbit all the way out to geostationary Earth orbit and beyond. And when we're doing that, we need to have multiple different sensors in orbit, and we need to be able to see when there isn't solar illumination as well. So in order to see when there isn't solar illumination, we can use radar approaches. So we can transmit a radar signal, and then through a number of different transmissions of signals, we can start to form images. And this technique has been used largely from looking down on the Earth. So taking satellites in orbit and doing what's called synthetic aperture radar imaging.
Yeah, I was going to ask, what is synthetic aperture radar imaging?
So synthetic aperture radar imaging enables you to see through cloud cover and through nighttime to be able to form images of the Earth that receive backscattered radar signals. So you transmit from a system and then you receive the backscattered signal. And from that backscattered signal, you can form an image. And that image uses compression to be able to get high resolution, essentially perpendicular to the satellite's trajectory, and uses the velocity of the satellite and the simulation of a very large antenna through using the satellite motion to generate good resolution images in the direction of the satellite velocity or in the azimuth direction.
Okay, so it's the movement of the satellite and the orbit of it acts as an antenna to get this signal. Am I in the right area?
In order to generate an image that's of a high resolution. If you weren't to perform processing in order to generate an image, you would need an extremely large antenna, so on the order of a kilometre, which isn't realistic.
Yeah,
so you have to use
huge.
the fact that the satellite's moving in order to simulate a very large antenna. In this particular project, instead of looking from the satellite orbit to the ground, we're looking from one satellite to another satellite. And this introduces another challenge in terms of the perspectives, because the relative velocity between your platforms is very different from imaging from a moving satellite to what's comparatively stationary Earth. Instead, you're trying to image using two very fast-moving objects in space. So typically, if you're looking in low Earth orbit, you're traveling 10 times faster than a speed of bullet, so really quickly. So being able to then form an image requires different kind of processing approaches that it requires using what's referred to as inverse synthetic aperture radar imaging. And this is an area of specialism of Marina's, so perhaps you can outline in a bit more detail, Marina, how you do the processing for inverse synthetic aperture radar imaging.
Sure. You rightly started with a synthetic aperture radar because audience usually familiar with that one much better. It's a remote sensing area. It's called Earth observation. So we want to make a very high resolution imagery of the Earth. Why we need to do this? Because we want to see if there is a change, for example, melting ice or change of the biomass and so on. And as you rightly said, to synthesize big antenna and therefore to improve resolution, we need a motion of the platform while the scene is stationary. So this is SAR. And now what we are doing, we also need to use a movement because this is the essence of SAR. We need to use movement of the platform for synthesizing aperture. But now we're inversing the problem. So we're considering the radar to be stationary, but the target instead, the object is starting to move within the beam of our radar.
To visualize this, the SAR is looking down, synthetic aperture radar is looking down at the Earth, and then inverse synthetic aperture radar is looking up.
It's looking up if we're talking about ground-based ISAR system, but don't forget that we are moving further. We are pushing technology further up. We are going to use this for in-orbit observation. So we are assuming
satellite to satellite.
Exactly, satellite to satellite. So we are putting our radar on another satellite, and it should be small. And we are making now use of the movement of the whatever object within our antenna beam, physical antenna beam. And when it's moving, the object is moving, and it should have radial motion. So we will experience a Doppler change and the range change of each point, and this Doppler and range change will uniquely define the position of the scattering point in our imaging map. Therefore, after the compression, we're compressing and each point will be mapped in its special representation.
Yeah.
So this is how we're forming the ISAR image, which is opposite to SAR imagery. Of course, both platforms are moving, so this is why ISAR from an orbit is starting to be even more complex, because we need to consider the motion, the mutual motion of two platforms.
Yeah, exactly. You're not looking from stationary up, you're looking from motion to motion.
Exactly.
And the speeds are so high, as we've said, it's 17,000 miles an hour. And that in itself seems like not just a mathematical challenge, but technological challenge.
So part of that challenge is thinking about being able to do things in real time as well. So the aim of this project is really to do a fully autonomous, novel mission. So think about how you would do every aspect of an inverse synthetic aperture radar mission if you were trying to do it autonomously, to be able to do things in real time, to reduce latency, to be able to do autonomous decision making. And when we're thinking about satellite missions, we think about every aspect of a satellite mission, from being able to task a satellite. So you're not always in active communication with a satellite. You're quite constrained in terms of your bandwidth. So you need to be able to uplink and downlink information. You also want to be able to do things without having to uplink and downlink information. You may want to be able to change your collection tasking, both in terms of what you're asking, where you're positioning your satellite and what you're asking your satellite to do, but also in terms of the way it's collecting the data that it's going to be using. With traditional optical imaging, you have maybe fewer parameters that you're able to control on the fly than with radar imaging. And you can actively change your parameters for radar imaging to change the kind of product that you're generating. So you can think of it not just in terms of generating 2D images, but you can also start to use multiple platforms to think of it in terms of generating 3D point clouds as well.
So, yeah, one thing which I wanted to say, that optical sensors will be always there. Optical sensors is unbeatable. But what is nuisance for the optics? Movement. Yeah, when you're moving within the field of view of optical camera, your image will be smeared. We instead are using these highly dynamic scenarios to make the imagery. So this is a beauty of it. We are basically using natural dynamics of the space to produce this imagery. And may I just say that how our project is actually, what is the title of our project and who is funder of this project?
Yeah, what is the title of your project?
The title of our project is AI-enabled satellite morphological inference from multidimensional inverse synthetic aperture radar data, Amelia. And it's funded by UK Space Agency.
I caught that you said Amelia.
Amelia, yes.
Yes, which is, for listeners who are unaware, my name is Amelia. It's spelled Aemelia.
Yes.
So Amelia rather than Amelia. But I think it was, Victoria, you told me, what's the reasoning behind that? Not just it's a great name, guys.
Typically, a lot of the space platforms in the UK are named after Shakespeare characters. And we're not afraid of risk. And we know that when you do things, there are a lot of errors that can occur. And we were looking for a name that was focused around digital twins, because the idea is to generate a fully autonomous digital twin that's taking real data and making decisions in real time. And Amelia in Shakespeare is in Comedy of Errors, and Amelia is mother of twins. So it seemed apt to use Amelia as the name for the project.
So yeah, we already accept that there will be errors and there will be confusions, but we are going to overcome it. One thing is, yeah, of course it's after Shakespeare, but it's also acronym. So if you will look at some letters in the full title, Amelia is also the acronym for our long, sophisticated title.
Yeah, I love a multi-use name. Excellent. And yeah, you had the other question, which was...
Dimensional.
Yes, what is multidimensional inverse synthetic aperture radar?
So the multidimensional aspect is that you can think of in a traditional SAR sense, where you transmit from one platform and then you receive your signal back at the same platform, and that's a monostatic setup. You can also do imaging engaging by transmitting from one platform and then receiving at a different platform. And that's a bistatic setup. And in that case, you can get very different features that are appearing in a bistatic setup compared with a monostatic setup. You can also have a multistatic setup where you've got more than 2 satellite setups, and you can start to transmit from multiple platforms to start to do complex things like beamforming. You can also think of multidimensional, also in terms of the frequencies. And perhaps, Marina, you can talk a little bit around the multidimensional frequency aspect.
Okay, so yeah, another dimension is a frequency. So first of all, we are first to push frequency very high up. No one did this, and we actually laid the foundation for sub-terahertz ISAR imagery. Sub-terahertz, we're operating at 300 gigahertz, let's say nominal, which means that we have only 1 millimeter wavelength. It is so small that it's starting to be sensitive to texture of practically any surface. And this allows us to get the imagery which will be very close to the optical one. We can penetrate through material, so we can get information about the material of some of the surface. So this is a frequency aspect of multi-diversity of diversity of frequency. But also we can use a different polarization of our interrogating wave as well. Can use left-hand polarized, right-hand polarized
What
wave.
does that mean?
Electromagnetic wave, if you remember from the school, it has electric vector and magnetic vector. So electric vector could nominally look up, vertical, or horizontally horizontal, but it also can rotate. Yeah.
Okay.
So it will be like a rotation, like a spiral with a rotational vector of this electric vector, and it could rotate to the right hand, like a clockwise or anti-clockwise. Will mean that it's right hand or left hand polarized. And each of these polarization will again, in a different way, highlight different surfaces and provide different contrast. So if we're using this diversity of polarization, we can increase double information about what we're seeing. And therefore extract more information about what the deployables, how it is made of, what materials it's made of, and so on.
Yeah, so it's using all of these different things like polarization and frequency to actually go under the surface of these satellites and objects in space and get more information, and whether that be for a threat or for information for governments. Sounds like an incredibly complex problem and also a very innovative solution. And I just wanted to touch upon what you said about what you mentioned about the autonomous side of this Project Victoria, because autonomous means no humans are up there. Is that correct?
So in some scenarios, you have satellite operators on the ground that are communicating with their satellite. But if you're looking at doing, for example, cislunar, you may not even be in communication with your satellite. And even if you're looking at it from a ground-based context, you may have intermittent windows in which you can uplink and downlink data. You're going to have trade-offs in terms of what you're able to do. So you're quite constrained in terms of how much power you have. So your ability to do processing. So perhaps, Marina, you can talk a little bit around some of the work that we're doing, trying to push things to do real-time approaches at the edge as well.
Yeah, absolutely. As you rightly said, that as soon as the space technologies are developing, humanity want to move further and further from Earth to the moon, to the Mars, and so on. At some point, communication with a control center on the Earth will be either too long to make a decision, for example, avoidance decision in a congestion situation, or it will be not possible at all due to some perturbations and so on. So what you need to do, you need to assess what's going on around of you and make a decision. It's pretty much like automotive radar. So every car is equipped with automotive radar. So, but the human brain is also in the car, so you can make decision yourself. In space, there is no human. You need to make an avoidance if the threat is detected and so on, with low latency, with very fast signal processing. So we are looking at making the processing not on the Earth as it usually was before. Instead, we will use edge computing platform to do all processing there. And we're estimating what it requires to collect the data, to make all this complex processing which we have, and then to move to the decision-making process, which is a big part of this project we're talking about. So we're going to classify the object, and we're going to create a decision based on what we observed.
It's not just one step ahead of we've got SAR, so we've got I-SAR, or Inverse Synthetic Aperture Radar. First, you're moving away from electro-optical imaging, then to Inverse Synthetic Aperture Radar. You're making it multidimensional, and then you're making this autonomous. So there's so many stages, and very logical stages, because obviously putting a human in space, or as you said, the uplink and downlink and the kind of the human latency could be catastrophic if there is a collision. But it just seems there are so many steps in this project. So how do you feel about that? How did you come to the decision to do everything at once, essentially?
We wanted a combination of delving down into the details on a certain number of areas, but also looking at a holistic view altogether as to how you would make it fully autonomous. So we're interested in a number of different use cases. So we want to reduce the probability of collisions in orbit. We want to think about how we do in-orbit servicing of satellite capability, thinking about refueling, but also thinking about things like threat assessment, counter space activity, building an understanding of the different sensor capabilities of platforms that are in orbit, thinking about their attitude or their pointing direction, being able to make predictions about space object behavior in order to reduce risk of in-orbit collisions or reduce risk posed by other platforms. So we want to be able to see if there are deployables or robotic arms on particular platforms as well. We're also thinking about specific scenarios in terms of specific orbital trajectories. So some of the scenarios we're looking at are things like an object flying by. So in order to do the imaging that we're trying to do, you have to think a lot about the orbital trajectories. And perhaps, Marina, you can talk a little bit more about the different scenarios that you've worked on in the past at the University of Birmingham and how we're developing them a bit further for this particular project.
Yeah, absolutely. So before I made an analogy that this radar in space will be like automotive radar, so we are just looking at everything around of us, so surrounding. But also, again, especially with the defense, so what we want to do, we want to look at non-cooperative resident space object. And I can give you one example. There is a Luch satellite. It was a Russian satellite which for a month was sitting next to Intelsat satellite. And because Intel satellite was not having any capability to see what is this Luch satellite, no one actually knows what it was doing. Was it an attempt of jamming or looking at the vulnerabilities and so on? Such satellites are called inspector satellites. They could be quite threatening. So what we want to do now, we want to design, we call it design a mission, to design an orbital deployment scenario so that we will be flying above of this particular object, and therefore we will produce during the observation time, which can last for tens of seconds, we will produce a sequence of these ISAR images, and all the images, all the frames will be made at slightly different angles. Therefore, we are getting like a nearly three-dimensional overview of the object which we're observing. So as soon as we are doing this, we will try to detect what capability this object has. Maybe it has a jamming antenna, or maybe it's a communication antenna, or something like that. So we want to classify all the features, all deployables, and be able to say what is the mission of this object, or if there is something threatening, we will be able to image and to understand what this non-cooperative resident space object is trying to do to our satellite.
I think it just puts into context exactly what you're looking for. And I wanted to pick up on that point and what you just said earlier about the risks, because you mentioned the kind of things that we could do with these autonomous missions and ISAR with refueling, threat assessment, attitude pointing, and also reducing risk. And I just wanted to delve a bit further on what are the risks? What are the risks of this kind of inspector satellite being there and not knowing the capabilities of it? What are the risks of collisions? We've touched upon it, but I would like to go a bit deeper into it.
If we look at UK registered assets and US registered assets, approximately 2,000 warnings a month are sent to UK registered assets about conjunctions that are occurring, so risk of potential collision occurring. And if you look at the US, you're seeing over 100,000 conjunction data messages being sent every year. So it's an increasing problem as we're seeing more and more launches into orbit. There's a higher and higher risk of collision. We're also seeing a growing counter-space threat, and we're seeing this space race occurring, or the sort of second phase of a space race that we're seeing with an explosion of capability. We're also seeing a change in the kind of space capabilities that are out there. So historically, if you go back 10 years, you'd need quite a large investment in order to be able to launch something into space. Increasingly, we're seeing the cost associated with that dropping. So organizations with a much lower investment can start to launch cubesats. We're seeing an awful lot of cubesats
What's
in
cubesats?
orbit. So they're much smaller satellites. So you can think of them as being smaller than the size of a washing machine.
Okay.
And we refer to them in terms of U, so 1U, 2U, 3U.
Yeah, they're
cubes.
It's not just a cube where payload, all the electronics is going to be hidden inside of this cube.
Yeah.
So it could be nano, it could be quite small, it could be 10 by 10 centimeters and even smaller.
Wow. So that, even harder to detect or harder to map, and it's getting even more crowded. We rely on satellites for everything from maps to risk assessment on the ground to pretty much everything we do nowadays requires the use of a satellite in terms of our national infrastructure and international infrastructure. So on one hand, maybe great that there's a cost drop that anyone can launch their satellites into orbit. But on the other hand, it just makes it even more crowded and the threat's that bit more nefarious.
Yeah, a lot of regulations are coming out because, there is a threat that they will be so crowded that you cannot put even more satellites. But there is another problem. The problem is related to electronic space itself, because with increase of satellites, and especially they are communicating to the Earth, interference is starting to be quite a significant problem. So electromagnetic background is starting to be so intense, and satellites are actually screening some of the electromagnetic signals coming to the Earth. So this is another problem, and another one, as I said before, is we are not only trying to avoid collision. We're also trying to observe if there is some hostile activities. And indication of that one could be that we are detecting very specific antenna directed to my satellite. It's phased array. Why it's directed at me? What's it trying to do? So this is why we want to understand what we need to do in this case. Should we roll and hide our vulnerabilities if we have one, or, for example, front end of our antennas and so on? So we need to come up with some decisions based on what we are seeing at very short distances, which are absolutely unavailable from Earth.
It's amazing to see as well how all of these themes almost cross-cut, because we're talking about objects in space, which seems quite abstract, very cool, very sci-fi. But then, as you talked about, these methods could also be used for volcanic eruptions. And also we talked about synthetic aperture radar, as in looking down, looking at monitoring things happening real time on the Earth. And we had a previous episode on sea ice and sea ice monitoring, which used that technique. And so it's amazing how these techniques are very multifaceted as well, and can be used to detect multiple threats, from environmental threats to human threats too. What has it been like coming up with this project, and what has the process and the journey been like?
So this project builds on a lot of previous work. So the University of Birmingham has done a lot in terms of developing the sub-terahertz sensor and doing a lot of in-lab testing and building of scenarios and the theory behind inverse synthetic aperture radar imaging. The Alan Turing Institute has a lot of underpinning work on how to do real-time detection within SAR images and how to do that on board in scenarios where you're quite very constrained in terms of the size, weight and power of your platform. That means you look at more modern approaches to doing edge AI, so looking at compressing your models, looking at techniques like pruning and quantization in order to make your models hundreds to thousands of times smaller so they can run in real time. It's been really fun working with the University of Birmingham. It's a good marrying of different expertise from an engineering department and an organisation that focuses more on the AI side of things. It's also very rare to get to work with another female PI within our domain, and it's really great working with Marina.
Yeah, I just want to, as any marriage, it all starts when you meet first and how we started to know each other. First of all, we've been familiar about the work, but then we have within the UK, we have a national, society, scientific society of all the experts in radar from academia, government, industry, of course. It's called MKIC. And I'm specifically founder of the focus group within this MSIC, which is called Radar for Space. And we invited Victoria to come for this radar in space, and it was in very exciting places. It was at the University of Birmingham, which is probably not too exciting, but then it was at Gunhill Station. And then we started to talk about that. One, what we can do together based on the similarity of our work. So this was very logical that we are starting to work with Victoria, with Alan Turing Institute, with her group.
Yeah, sounds like a very fruitful marriage and a very positive one. Then the question, I guess, is what's next? What's on the horizon for SAR and SDA?
So to date, I think we've done a lot of developing of the generating large volumes of simulated data so we can train machine learning algorithms to do segmentation, classification, detection. We've also thought about how to track features through time using AI approaches. Further along in the project, we're interested in looking at making these approaches really efficient, so focusing on the edge AI component. Thinking about not just a universal model, so thinking about foundation model capability, but also thinking about specialized agent approaches, and then moving from specialized agent approaches where you may have a particular task that you're training to be specialized on, thinking more about an agentic AI system.
What you're saying, it's autonomous systems should be self-coordinating, right? This self-coordination should be based on reliable data. So if our ISAR imagery provides this reliable data, as well as optical imagery, we're not denying this, then you can, each satellite as a system is starting to reconfigure to avoid collisions and on a global scale. It's pretty much like a bees or ants. They are coordinating. If one is sensing something threat, it will propagate and the whole community of ants will know about this threat. So this is what we're going to do as well. So as soon as there is a constellation in space and it's autonomous, we want detected threat or detected collision to be propagated.
This project is doing multiple things well and also rethinking existing technologies in a very clever way, which for me is really exciting because it's something that you can prove already exists and you're improving it further. And then I'm a big sci-fi fan as well. So having fully autonomous space missions and clearing up objects is crazy. I remember, this is probably going to get cut, so I'm just telling you my anecdotes. Have you read or watched Project Aemelia by any chance? The main character was in one spaceship trying to find a main character in another spaceship, and it was a very tense moment. The other character was going to die if he didn't find him soon. And so he used optical imaging, but by using the flares of his spaceship to turn around and basically do it in one axis, then another axis, until the flares of his ship finally glinted off his friend, and he found his friend and managed to save him. Not ruining anything for you because it's a great book, but again, we're talking about optical imaging, and to see, and this is sci-fi, and to see you guys do it in real life is very cool.
I also a fan of sci-fi. I don't know how it's Victoria. And one of the best movies of all time, and book as well, by Arthur Clarke, and the movie is Space Odyssey 2001. Do you remember when they are on a mission to Jupiter? They are losing one of the astronauts, which was hit by the broken arm of this like a maneuverable spacecraft.
Yeah.
On that one, and he's losing that one. They cannot see where it is, and they're only using optical camera.
So what you're saying is that if Dr. Ryland Grace or Commander David Bowman had the imaging capabilities of Project Aemelia, they would have found their comrades faster.
Yeah, this is where you need more sensor, you need more capabilities to look around and to detect it at a longer distance when it's not illuminated.
Yeah, so basically I think someone needs to write a sci-fi book using your technology now. That's my conclusion from this. It turns out that keeping the peace on Earth's orbital highways requires a completely new way of seeing. From tracking coin-sized debris in the pitch black to using inverse synthetic aperture radar to map satellites in real time. Shifting our perspective from ground to space to space is changing everything. And as we heard, it's not just about avoiding collisions. This is the same AI-driven radar technology that is keeping watch over climate change, disaster zones, conflict areas right here on the ground.
It's an incredibly exciting frontier and a brilliant testament to the teams at the Alan Turing Institute and the University of Birmingham, where we're driving the future of UK space technology and automation. A massive thank you to Professor Marina Gashinova from the University of Birmingham for guiding us through the cosmos today.
Thank you, Marina.
And thank you very much to you. It was an enjoyable experience. I loved it.
And if people want to find out more about this project and actually see some visualizations rather than just imagining it, where can they go?
First of all, they can read our papers because we are publishing. Also, we have some website information, so people can look at our profiles and see information about this project.
You can find all the papers that Marina just mentioned in the show notes. So a huge thank you to all of you listening to this episode of the Turing Podcast. If this episode gave you a new perspective on the invisible world above us, make sure to subscribe, leave us a rating, share it with a friend who's interested in AI. So until next time, I'm Amelia Jabry. Clear skies, take care, and we'll catch you on the next episode.